In this video, we're going to talk about mixtures and movements of gases. So our next formula is called Dalton's law of partial pressure. And it says that for a mixture of gases in a container, the total pressure of the gases in the container is equal to the partial pressures of each component gas. So P1 here is the partial pressure or contribution of the first gas, P2 would be the second gas, P3 would be the third, so on and so forth. So if the first three containers here are all gases and they're put into the fourth, we can find the pressure in that container by adding up the pressures in the first three. So if container 1 was at 2 atmospheres of pressure, container 2 was 1 atmosphere, container 3 was 3, and if I put them all into this fourth, the P total here, using Dalton's law here, would just be very simple to find. We just add them up. 2 plus 1 plus 3 is 6 atmospheres of pressure. Now we can do this to find P total, or we could use this to find an unknown partial pressure of a contributing gas if they give you P total, like in this next example. The pressure of a mixture of nitrogen, carbon dioxide, and oxygen is 150 kilopascals. What is the partial pressure of oxygen if the partial pressures of the nitrogen and carbon dioxide are 100 kilopascals and 24 kilopascals, respectively? So they've given us P total. And it's equal to the partial pressure of each component. So they've given us P total in the math problem. It's 150 kilopascals. They also give us the pressure of the nitrogen. It looks like that is 100 kilopascals. And the carbon dioxide is 24 kilopascals. And they want to know the partial pressure of the oxygen. So to do this, we just need to isolate the partial pressure of the oxygen by subtracting both sides by 100 kilopascals plus 24 kilopascals. On the right, they will cancel and leave us with the pressure of oxygen. On the left, 150 minus 100 minus 24 is 26 kilopascals of pressure. Next, we're going to talk about diffusion and effusion. Diffusion is when molecules move from areas of high concentration to areas of low concentration. You may remember this from biology, talking about the fusion of molecules across a membrane. Effusion you may not have heard of. Effusion is when gas escapes through a tiny hole in a container. So if you got a hole in your car tire, gas doesn't diffuse out of your tire, it effuses out of your tire. Same idea, slightly different word. Both of these depend on the molar mass of the particle, which determines the speed. So let me go back here. So this picture is showing diffusion. So in this first box here, the red particles are on one side, the silver particles are on the other side of a non-permeable membrane. If that membrane all of a sudden becomes permeable or we take it away, they start to mix. The red ones are going to move to the right and the silver ones are going to move to the left. And they do this just naturally on their own molecular movement is just going to spread them out as they move. The speed at which they move is dependent upon how heavy they are. The lighter the particle, the faster it moves. The heavier the particle, the slower it moves. This next picture shows effusion. So if I have this container here, and this side is charged with gas, and this side is under a vacuum, if we create a pinhole in here, now the gas in this side has a place to go. And because of the random molecular motion of these particles, they will eventually move through this pinhole and start to move into this chamber on the left. And again, the speed at which they do this is dependent upon how heavy those particles are. So the rate of effusion and diffusion can be quantified. It is inversely proportional to the square root of the molar masses of those molecules. So this is what it looks like in a formula. So the rate of gas A compared to the rate of gas B is equal to the square root of mass B divided by the square root of mass A. So this is the inverse relationship here. So whatever gas you have on the top, when you're comparing them, you need to remember to put on the bottom. You also need to know how to use your square root key correctly on your calculator. Some calculators you have to hit the square root first, then the number. Other calculators you have to hit the number, then the square root. So figure out which one yours is by watching these examples. So here's the problem. If equal amounts of both helium and nitrogen are placed in a porous container and allowed to escape, which gas would escape faster and how much faster would it escape? So which gas would escape faster should be easy to answer. That's going to be the lighter one. That's obviously helium. You can look up these molar masses on the reference table. Helium weighs less than nitrogen. But how much faster, you need to use Graham's law to solve for this. So here's Graham's law again. Rate of A over rate of B is equal to the square root of mass B over the square root of mass A. Remember, you got to flip them. I've seen a lot of students make the mistake of doing the numbers correctly, finding the molar masses, but not finding the inverse relationship, not flipping them. Okay, so here's a tip. Always arrange your gases so that you're comparing the lighter one to the heavier one. If you do it the other way around, you're going to get a decimal. And it's not that that's wrong, it's just that it's a little more awkward to say that the nitrogen would move a third as fast as helium rather than helium moving 3 times faster. We like to use whole numbers in Graham's law problems. Again, you won't be wrong if you do it the other way, but it's helpful to always compare the lighter gas to the heavier gas so that when you flip them, the heavier number is on top and the lighter number, and you get a whole number when you do your division. Okay, so here's how it's set up. We're going to do the lighter gas, helium, compared to the heavier gas, nitrogen. Now remember, nitrogen is diatomic, so it's N2, not just N. The square root of N2 is 28. Nitrogen weighs 14, but we need to do 14 plus 14 for N2. It's another common mistake I see on Graham's law problems. If you use a diatomic gas, which a lot of them are, and you don't remember it's diatomic, you're going to get your numbers wrong. So 28 is the square root of 28 grams divided by the square root of 4 grams. Helium weighs 4. And if you use your square root keys correctly, that is 5.3 divided by 2, which is 2.65. Now in Graham's law, we like to round up to the nearest whole number. If you left it at 2.65, I wouldn't mark you wrong, but traditionally how this is done is you always round up to the nearest whole number. We say it effuses about 3 times as fast as nitrogen would. So in summary here, gases often exist as mixtures. The total pressure of the mixture can be calculated using Dalton's law by adding up all the component gases and individual pressures. And diffusion and effusion describe how gases move. Obviously, lighter gases move faster than heavier gases, but this can be quantified using Graham's law. Make sure you do it correctly. It's a really easy math problem, but it's easy to mess up. Make sure you always compare your lighter gas to your heavier gas, and don't forget to flip your masses when you are solving. Always have the inverse relationship. So that's it for this gas chapter. If you have any questions, please let me know, and I hope this makes sense.